the science of chemistry. For many, it is a synonym for the synthesis of molecules and compounds. For others, however, it is representing theoretical descriptions utilizing classical and quantum mechanics, as well as molecular investigations using spectroscopic methods. Spectroscopy, which is describing a significant fraction of physical chemistry, is presented here for applications and interest in ongoing research. In teaching, it is initially of minor relevance, but is quickly gaining interest after finishing undergraduate studies. In an application of linear spectroscopy, it is, for example, possible to investigate the solvation shell surrounding molecules of interest. Hereby, a sample spectrum is compared to a pure solvent spectrum, which subtraction provides the spectrum of solely the solvation shell surrounding the probed molecules. In another set of experiments given by time-resolved measurements, it is possible to investigate lifetimes and excited state dynamics. Via the use of a pulsed laser, a change in the molecular system is induced, which is detected with a consecutive laser pulse. Through the delay between the two pulses, it is then possible to obtain time-dependent information, giving rise to the energy landscape of the molecular system. In working groups of physical chemistry, there are also non-linear experiments taking place, where processes with more than one photon happen simultaneously. One example for such an experiment is given through some frequency generation in which molecules at interfaces are investigated and their orientation determined. With the help of non-linear phenomena, like the generation of a plasma, it is possible to create electromagnetic radiation through which molecular vibrations spanning the whole mid-infrared region can be detected. These occur on a femto to picosecond time scale. 1 femtosecond is, as a reference in comparison to 1 second, as short as 1 second compared to the temporal distance to the dinosaur age. For many applications, the polarization state of light is of great importance, which can be modified using polarizers or birefringent material. Will, for example, a quartz crystal be moved between two crossed polarizers, then light passing through can be rotated depending on its angle, so that it can transmit through the second polarizer. As the crystal is having a gradient, depending on the thickness of the crystal, different colors will be transmitted. For a fixed delay, so a given crystal thickness, it is possible to transmit different wavelengths depending on the orientation of the polarizers. And next to building optical setups, it is possible to motorize, optimize, and program processes to capture and analyze spectra efficiently, or to use already existing apparatus to investigate a set of manifold systems and understand their behavior.